Okay, let us start our first seminar in this year. So, welcome to welcome to the first ITMP seminar in 2025. And today our speaker is Christopher Couzens from Mathematical Institute, Oxford. We'll speak about localizations in Roman supergravity.
Okay, thank you for having me. It's nice to be the first of your seminar series for the year. Um, so I'm going to talk about some work that should hopefully be out very soon, which is with Carolina Mata-Gregory and her MSc student, her master's student Davide Muniz in Brasilia, James Sparks in Oxford, and our PhD student Tabea Sipa. Um, so I am going to encourage you to ask as many questions as possible. So I've tried to give an overview of what this localization means, but please stop me at any point if you have any questions at all. Okay, so what the basic question that we want to try and answer is if we're looking at supergravity things or supergravity solutions, it's very hard to actually solve Einstein's equations. But the nice thing is that sometimes we don't actually need to solve Einstein's equations. So there are some observables in ADS-CFT or even black hole thermodynamics where what you want is just some integral over your space-time or some subspace of your space-time. So an example of this would be something like the on-shell action. So here you just take your action for your supergravity theory, and then you just literally plug in the solution of Einstein's equations into this, and you get some result. There's some subtleties with regularization and all these things, but for the moment, let's just ignore these subtleties. And then you get some result. And in field theory, this is something like computing the large N index from the field theory side. So this thing here seems quite nice. It's just some integral over your space-time of some very simple things, the Ricci scalar and things like this. But this looks very dependent on knowing the metric. So it seems very dependent on also solving Einstein's equations. But there's been a nice development which kind of says that for some observables like these, this isn't actually necessary to solve Einstein's equations. So there's quite a rich history of this, which goes back even to like 2005 for doing things like computing the volumes of Sasaki-Einstein manifolds. But I'll ignore this as prehistory and talk more about this more recent method, which uses equivariant localization. So the first kind of paper for doing this in supergravity was very recent, in 2 years ago, by Benetti Giannellini, Gauntlet, and Sparks. And the rough idea is that you're going to look at some supergravity background which has some symmetry. And you're going to use this equivariant localization, which essentially says that integrals receive only contributions from the symmetry fixed points. So they localize to the points, fixed points of your symmetry. So schematically, what you have is something like this, where you have your observable, it's some integral over your space-time or some submanifold, and all you get really are just a sum over some fixed points, which I'll explain a bit later. And in this case, if it's very simple, it's just sum over some scalar quantity. So the reason why this is very nice is to do all of this, you don't actually need to know an explicit solution. So I don't have to solve Einstein's equations at all. What happens instead is that the result depends just on topology. So I can just say, I want to consider some background with this particular topology. I can just crank my mechanism and I just plug in this topology data. And from here, it spits out an answer for my observable. And this is very uniform for doing it. So I have to do a bit of work in the beginning to set up this machinery. But then once I've set up this machinery, I could just throw in any kind of different topologies that I want. It's a very little bit of work to do afterwards, and you keep getting different the results being spit out very easily. So it's very general. So I take my supergravity theory, I have one thing, and I can just keep plugging in different topologies and getting nice new results. Okay, so the main tool for doing this is equivariant localization. So I thought we could just do a kind of a proof of why it works. It's surprisingly simple, um, and it needs a bit of differential geometry, but not too much. So what we want to do, compute some integrals over some manifolds, and we assume our manifold has a symmetry group. So this is a very weak requirement. It's not completely unreasonable. So we're going to consider a 2n dimensional manifold without boundary. So the fact that it is 2n dimensional just makes things a bit easier. You can also do this for odd dimensional manifolds, but it's slightly different in a way that won't be necessary for us. And this without boundaries is also not super important. You can also take into account contributions of boundaries. And I actually have a paper on this with Alice Lucia, where we looked at trying to do this with spaces with boundaries, and you get some nice results there. Okay, so we're going to say we have a symmetry, and with a symmetry, we have some killing vector field, which I've denoted by psi here. So it's just the usual condition. The lead derivative of the metric vanishes along this direction, or you can have it as the connection acting on your killing vector field symmetrized to zero. So you could take it to be some non-abelian symmetry that you have, but just for simplicity, and because this is what we'll need in the Romans example, we'll just assume that this generates some U1 isometry. And then what we want to restrict to are integrating forms, which I'm going to denote by this phi, which have vanishing lead derivative along this killing vector field. So I could put any kind of function. I could then multiply this phi by any function I wanted, as long as it doesn't depend on the coordinates of this killing vector field. And this just allows us to actually compute stuff. So if it was no longer a killing vector of this phi, you wouldn't be able to apply these results. So what you need to do is you need to replace what you would call by cohomology with what is called equivariant cohomology. So the way you do this is quite simple. So cohomology is groups where you have your exterior derivative d, and you look at things which are closed under d modulo the exact pieces. And now you just replace this exterior derivative by this twisted derivative. So here the d is just the usual exterior derivative again. And now what you have to do is you have to minus the contraction into your form with this killing vector psi. So you should recall that the exterior derivative raises the form degree by 1. And because you're doing contraction, you're going to decrease the form degree by 1. So rather than considering forms, what you have to consider are things called polyforms. So these are just forms where you have mixed degrees. And so that you could get something which is equivariantly closed, you'd have to have forms which basically differ by 2. So if I act with the contraction on this, I'm going to get an n-1 form. And so I would have to have an n-2 form here, which could do something with once I've acted with d on this. So in general, what we want is something which is nilpotent to define some cohomology class. But in general, this d psi is not nilpotent. So if you take the square of it, what you get is the lead derivative along psi. And this you can just see by using Cartan's magic formula. So what we're going to further restrict to are exactly these polyforms phi, which have vanishing lead derivative along psi. And with this restriction, what you have is that this d psi is nilpotent. So this is really why we needed to impose this here, is because with this restriction, we can now define some equivariant cohomology. So what we want is now something which is equivariantly closed as opposed to just closed in the usual sense. So what you have is that this top form of this polyform should be closed. There's nothing that could act to give a contribution over here. Whereas for the lower degree forms, you get this kind of relation. So the contraction of the form with degree 2 plus 2 is equal to the exterior derivative on this form of degree n minus 2, and so forth. So you get a nice chain of this. So what you should do is, given a particular closed phi n, I can then use this descent kind of procedure to construct the lower degree forms in my polyform. So this isn't going to be unique. There's going to be different ways of doing this. You can add in constants essentially at every step, or closed forms. But what you need to require here is just that these forms that you get are well-defined. And any well-defined forms, and if you have the same different construction of a full polyform, and you do these same tricks, the end result of the polyform you have may differ, but once you do integrals over these things, they're just going to be differing by exact pieces, so the results are going to be the same. So we have the same kind of exact forms. They're called equivariantly exact if the phi is equal to d psi of some well-defined polyform psi. And this now allows us to define this psi equivariant cohomology groups, which is just essentially the same thing as usual, but now rather than the exterior derivative, we have this twisted differential. So the nice thing is that if this psi acts freely, so it has no fixed points, this would just be the ordinary cohomology on your space modulo your symmetry. So in what I've presented here, it'd be your space modulo some circle action. So this is a bit formal, but the reason why I introduced this is to see why this is going to be nice. So we want to have some integral over some 2n dimensional form, which is the maximal form on our spacetime. And what we're going to say is that this is the same as integrating this polyform phi, which has all of these pieces, so 2n, 2n minus 2, so forth. So when we define this integral, what we really mean is pick out the form which has the same degree as the dimension of what you're trying to integrate over. So we're always going to be interested in top forms which are closed but not exact. So the reason why is this will give us something which is a nice observable. It's not going to depend on the homology cycle that you've taken to compute the integral. This is just the usual law that we do. But the nice thing now is that we have this polyform phi, and we could add in some equivariantly exact thing. So this phi should really be a psi, sorry. And the nice result is that this integral is exactly the same as the integral of this phi. So I can add in equivariantly exact pieces, and it doesn't change the result. So this is like the usual thing with just normal cohomology. If I take some integral, I can add exact pieces to the integrand, and this doesn't affect the result of my integral. So we get that the integrals just depend on the equivariant cohomology class and not the representative. So now we can try and see why these integrals should localize. And the statement is that these integrals will localize to the fixed points of the symmetry. So we define this fixed point set, M psi, to be all the points in our manifold M where the action of this psi at that point acts as 0. So it does nothing. It leaves the space invariant. So we now want to do this integral over our spacetime M of this phi. But what we can do is we can add in these exact pieces. And we can add in these exact pieces in a smart way by defining this phi t, which is just phi wedge the exponential of some exact piece here. So we have some freedom to choose what beta is. And this freedom is that we can choose any beta which is well-defined and satisfies that the lead derivative of it along this direction psi vanishes. So if you take the t derivative of this phi t defined in this way, what you find is that it is a globally well-defined thing here with the exterior derivative, the twisted differential applied to it. So this is something which is equivariantly exact. So what this means is that the integrals that we're going to do for this phi are the same as the integrals that we can do with this phi t for all values of t. So if you've ever seen how you do the proof of supersymmetric localization, it works very much the same thing. You modify your action with some Q exact piece, which is roughly what this thing here is doing. And then you're going to choose this parameter t to make things as nice as possible. And this is doing exactly the same. So for t equals 0, we have back the original integral. But because we can evaluate it for any t, we're going to choose to take this t to infinity limit. So what we should do is we should take some beta so that this d psi on beta for the 0 form is something which is semi-negative definite, and we want the maximum of this to be equal to 0. And then what's going to happen if we take the t to infinity limit is that the contributions that we're going to get are going to be sharply peaked where this 0 form piece vanishes. And they're going to be suppressed everywhere else. So the smartest choice that you can make, but by means not the only one, is to take beta to be equal to this eta, which I've just defined to be the one form you get from bringing down the index on this killing vector psi. So you get this nice one form. And the reason why this is nice is because if I plug this all in, I take the t to infinity limit, and I compute this phi t, what I have is that this is just phi wedge this exponential of some 2 form times the exponential of this minus t with the norm of my killing vector psi. So you may be worried that this has some exponential t here, and if I take this t to infinity limit, this is going to not be so great. It's going to compete with this bit here. But you should now do the series expansion of this term, and you see that this is just going to give you polynomials in t, which is still going to be suppressed by this exponential factor when you take this t to infinity limit. And also you can notice that this has to terminate because the eta is a 2 form, and you can have at most n of these without making it 0 identically. So what you see now is that when we take this t to infinity limit, this e to the minus t norm of psi squared is going to basically act as a delta function, and is precisely going to give us contributions when this norm of psi vanishes. But this is nothing but the points in this m psi. So with this kind of nice argument, what you can see is that when you have a symmetry and you consider things which are equivariant with respect to this symmetry, the contributions you get from all integrals are precisely where this symmetry acts trivially. So now we want to actually use this and to actually be able to compute this. So far I've told you that the integrals localize, but I haven't told you how to actually compute the contributions from this. So we're going to take the simplest example. And the simplest example is that we have fixed points. So for example, we could have a two-sphere, and we could take the killing vector to be the one that rotates around the z-axis. So these lines here are the action of this killing vector, and you see that at the north and south poles, this action has fixed points. So this action does nothing. So these are fixed points because they are essentially points in your space. So if we were to take some more general manifolds, so high dimensions, if we zoom into these fixed points, what we see here would be R2. So this is kind of like what signifies that it's some kind of fixed point. So if we were to take a high dimensional manifold, so our 2n dimensional manifold M, and we zoom into such a fixed point, what we're going to get is R to the 2n. So we can introduce a set of nice coordinates at this point P, which are these Cartesian coordinates where we basically break up this R2n into n copies of R2. And we introduce these adapted coordinates, which are basically polars for our two-dimensional R2 space. So the killing vector that's going to generate rotations around this fixed point for each of these R2 copies is precisely going to be this phi I. So partial phi I would be the killing vector. So locally around this point, the metric just takes this flat space form, and in our nice Cartesian, our nice polar coordinates, we have it takes this form here. So the fixed point in terms of these coordinates is precisely when all of the ri's are equal to 0. And the killing vector that we have now takes this form here. So this is it in Cartesian coordinates, and this is it in our nice polar-like coordinates. So the important, was that a question?
Do you understand correctly that here in reality you have n independent killing vectors?
So in this case here, you wouldn't have n. Okay, in how I'm drawing it now, I would have n independent killing vectors, but the real killing vector that I'm considering is this psi here, which is now a combination of these n independent killing vectors.
But then, like, if you have only a single killing vector, then do I understand correctly that it reduces the number of integrations by 2? Let's say if you consider a single U1 in n-dimensional space, then fixed points are n minus 2 dimensional.
No, not always.
Not always.
So so what you should think of it is that if I have a fixed point of this killing vector, I may have just one killing vector, but it can be at certain points that you have like these what do I want to say? Emergent symmetries effectively. Whereas, so essentially it still looks like R4 at this point. For example, I could have a 4D space where I have only one killing vector, but at some point it looks like R4, and then effectively I have two killing vectors from this viewpoint.
Okay.
But they're not globally well-defined killing vectors. Only this U1 that I'm localizing with is.
Okay, thank you.
Yeah, thank you. So this is a particular choice I could make where I have these fixed points, which basically gives it to me. If I zoom into this metric, it looks exactly like R2n. So these B's here, we're going to call them weights. They're basically telling you how fast you're rotating in this particular R2 plane. So this is how this psi is going to act on these coordinates. It's going to take these Cartesian coordinates and act with this matrix. And you see that these B's here are basically telling you how quickly you're rotating these coordinates. So the final thing we need to do, so we can actually compute this integral, is to work out what this one form eta was, which appeared here. and also what this d eta is. So if you can compute this d psi of eta, and if you expand it around this fixed point, what you find is this two-form piece here and this nice one-form piece here. So you see that it's just going to be the squared of these weights times by this r squared coordinate. And all that remains to do is basically plug this back into this formula here and compute. So if I do this, what I end up with is, so now I'm integrating now over this R2n at this fixed point. And what I end up with is I pick out the zero form piece of this phi. I have a product over these t's and these bips, these weights. And now I have n integrals over R2, which are just, if I write it in these polar coordinates, a trivial integral over my circle direction in R2, and then a nice Gaussian integration. So I can just do all of this. It's very simple just to do it. And what you get is this nice result here. So if I have just a fixed point, the contribution from that fixed point is precisely evaluate this zero form part of my polyform at the fixed point, multiply it by 2 pi to the n, and then divide through by the product of all of these weights. So this is for isolated fixed points, ones which look like, if I zoom in, R2n, where 2n is the dimensional manifold. And if I just had all of these different fixed points, all I have to do is basically sum up all of these integrals, all of these contributions here, and then I have exactly the result of my integral. So it doesn't have to be isolated fixed points. You could have things which aren't just fixed in a point, but they're fixed in surfaces. So a trivial example of this would be the Schwarzschild metric. So I could take some killing vector, which is my time direction, for my time direction, partial t. And then I could look at, where does this have a zero? Well, it has a zero at the horizon where f of r is equal to 0. And if I zoom into this place, what happens is the metric looks like something like r11 plus a constant multiplying my s2. So this is no longer a fixed point. It's what we would call a bolt or a two-dimensional fixed surface. So I can take any value, any point on the S2, coupled with this R equals RH, and this gives me some surface which is basically left invariant by this rotation by dt. So we have to take into account not only just fixed points, but all kind of dimension fixed point loci. So for us, what happens is they're always going to be coming 0, 2, 4, 6. There's a theorem that tells you that there has to be even. So we have to take into account the contributions from all of these different dimensional spaces. So the fixed points with the zeros, and this example here would be a 2. So if you do all of this, and you take into account all of these extra contributions, what you would end up with is the BVAB theorem. So this is Berlin, Verne, Attia, and Bott in 82 and 84. And the statement is just what I've tried to explain in the first half hour, which is that the integral of some equivariantly closed form localizes to the fixed points of the symmetry. And what you get is this somewhat mysterious looking formula. You have the thing that we care about here. You have some sum over this fixed point set. So this was this m psi. You have your polyform here, phi, and you're now pulling this back onto this fixed point surface. And then you just have the Euler form of the normal bundle to this surface. So this looks deceptively simple / scary at the same time because there's funny things happening. But we can just try and go through some of the language there. So I've kind of explained what a fixed point set is. It's just where some action on your manifold basically starts acting trivially, and psi is equal to 0, the killing vector we care about. So the normal bundle that appears in this N here is basically we have this kind of image here where it's our manifold. This sigma here is basically left invariant, but it's not shrinking to 0 size. And what's left is that this psi rotates things in this normal bundle, which is this flat piece here. And this is roughly what's going to look like Rn or R to some power to some power. So this last statement is not fully true. You could consider something more general, but just for ease of completion, ease of like computations, and because this is what happens in all of the examples we're going to consider, we'll just make this assumption that this normal bundle splits into these nice copies of R2. So we just call each of these copies of R2 this line bundle Li. The final thing is this Euler character. So this is the equivariantly completed one. And if you take this assumption of these normal bundles, how it splits is you just get a product of the first Chern class of this line bundle, Li, which is roughly R2. And you get this contribution here, where this epsilon I is the weights of the action of this psi rotating in these R2 plane. So this was precisely these BIs that appear here. These are these weights, and it appears here in this Euler bundle. In the Euler class here. So the only other subtlety is that you're now dividing by a form. So this looks really stupid, but what you should think of this is you just use a series expansion of 1 over 1 minus x. So these are going to play the role of the 1 up to some normalization, and then you just get a series in powers of different forms. So if you put all of this together, you take this formula here, plug all of this in, you get this horrible looking mess. And this just looks absolutely awful. But let's just look at the first term here. So this is the dimension 0 piece. So this is the fixed points. And all we just see is what we had from before when we did this kind of proof by using this Gaussian factors. So we have the phi 0, the zero form piece, evaluated at the fixed point. We just have these 2 pi to the n, and then just the product of the weights. So let's just go one more. So now, rather than having fixed points, we have some two-sphere, or essentially a two-dimensional surface, which is left fixed. And here we have n minus weights. We integrate over the fixed surface that we're left with, this phi 2, and then we have to also do an integral over the first Chern class of this line bundles. So you haven't quite got as nice a result here. It's not completely fixed. You still have to do some integrals. But the nice thing is that this integral is simple. It's just some Chern class. And this one you can almost always do. So it has reduced the difficulty from doing a 2n dimensional integral to something in far less dimensions. You could keep going up in order, it just gets more complicated, but there's kind of you can see the nice kind of pattern happening. So let's just do an example, and let's do like the most trivial one, which is just an S2. So this is cheating a bit, and it's more just, I don't know, a better way of showing you how to do it without having an explicit metric to begin with. But let's just consider a two-sphere, and we have this usual metric on it. And what we want to compute is the volume form. And we're going to do it with this localization. So we need some killing vector, and the killing vector we're going to have is this partial phi, which is doing these rotations around the S2. And now we just need to compute this polyform. So we have just to compute this phi 0. And you can check quite easily that if I contract in partial phi into this here, this is my phi 2, I'm just going to get sine theta d theta up to a minus sign. And so the phi 0 is going to be something like cos theta. And if you wanted, you could just throw in some arbitrary constant. So this has given us our polyform now. Now we just need to identify the fixed point set. So it's going to be precisely the poles of this S2 where this action is trivial. So we have two of them. And then I just need to plug it into this formula here. And all I'm going to have is the contribution from here. And it's just going to be, I take 2 pi, divide by the weight, and evaluate phi 0 at the fixed point. So 2 pi weight at the North Pole, phi 0 at the North Pole, plus the same for the South Pole. So the only difficult bit that remains is to work out these weights. The weights are just telling you how quickly you're rotating. So I can just fix this to be 1 because there's a no thing here. But the only other difficulty bit here is thinking about the orientation. So if I'm at the North Pole and I'm saying this has weight 1, this is going anti-clockwise. If I now look at the South Pole, this is going clockwise. So here I will give it a weight 1. And it means here I have to give it a weight -1. So if I plug this all in, I put the weight 1 here, I evaluate cos at 0, same thing with pi, and I do get exactly my 4 pi. So I will say again, this is a stupid example. I already have the metric. I can do all of this without having to kind of use this technology. But the point is that it's quite simple in the end what you have to do. You just have to know a bit about the space that you work in, where are the fixed points, what kind are they, and what are these weights. So you can do some more complicated ones. I won't do much of this, but I just wanted to say there's a nice kind of different thing about this. So if you consider CP2, here's the metric from CP2. Now I have some choice. I could choose some killing vector, which is a combination of the killing vector partial psi and the combination of partial phi. And depending on what these values of B1 and B2 are, if I set one to 0 and the other not, I get different types of fixed point sets. So for example, if I just considered partial psi, so here, the norm of this is sine squared cos squared. So I'm going to get some kind of fixed point set at zeta equals 0 or zeta equals pi over 2. So we see that at zeta equals 0, this bit shrinks and this bit shrinks here. So this is going to be a fixed point. At zeta equals pi over 2, this bit remains finite size. So we get a codimension 2 fixed point set. And it's this 2 sphere is basically preserved, is not rotated upon, but everything else you get here. So it becomes something like R2 times S2. Conversely, if you picked partial phi, you would have 3 fixed points. So you could pick the zeta equals 0. Sorry, these shouldn't be psi's, they should be zetas. You get zeta equals 0, but you could also have the poles of the 2 sphere coupled with, to get rid of this term here, zeta equals pi over 2. So here you have a fixed point and a 2D, and here you just have 3 fixed points. So you now should compute the polyforms. They'll be slightly different because you're contracting them with a different vector field. And you could basically add in loads of different constants. So if you do it with psi, you get something like this for the polyform. You see I've introduced some constant here. And you just plug in everything you have, and you find that you get this result. And it doesn't actually matter which of these killing vectors you do, you get the same result, despite them looking very different. So this is very powerful. I haven't given you a good example of it being powerful. So that's hopefully what I'll be doing next, unless there are any questions.
Concerning the previous example, can you apply your trick twice? So you first use the first killing vector, and then like you reduce the integration to its fixed points, and then you apply the second one to further reduce it. I don't know, to
So
something.
so you could, if you have some manifolds with multiple killing vectors, you could apply you could use this basically for multiple killing vectors. Here you don't need to, but in principle you could. There's no objection. You could add in multiple different killing vectors to do this.
Mhm.
Uh, can you localize on the killing horizon where xi squared equals to 0 and Lorentz signature? I just didn't catch probably.
Yeah, you can do this. So really, you should do it in Euclidean space, but if you wanted to, you could do it in Lorentzian as well.
Yeah, if I have a Lorentzian spacetime and I calculate a four-dimensional integral, like in four-dimensional spacetime, so you will localize me on the black hole horizon like a light-like surface.
So here I was a bit too cavalier. Really, I should be using something which is a U1 action, whereas when I have the short shield, it's really an R action. So I would technically get some infinite thing here, but really I
Okay.
should wick rotate. I should wick rotate, then you'd get a good result.
Mhm.
Yeah, sorry, that was me
Thank
just
you.
being a bit cavalier with my example.
What about the ADS, which is periodic in time? You
So
have a
here it
periodic.
works. So here we do it, but really we do it in Euclidean space.
Okay.
We constantly wick rotate, but there is no actually objection to doing it in kind of these spaces. It's just you have to be careful with like whether it's a circle action or an R action.
Okay, thank you.
And can you explain what goes
Okay.
once you have not a circular action, but I don't know, let's say translations in flat space? It doesn't have any fixed
Basically,
point.
it just becomes infinite, essentially. You can see it go where it's going to go wrong is that you don't quite have this nice splitting like this anymore, and this one would essentially become infinite. I think is the issue.
Mhm. And another thing, I don't know whether probably it has some connection with things like, I don't know, maybe Fourier transforms or something. Because anyways, you have some integrals remaining. So it feels
Hmm.
like you just use symmetry to reduce the number of integrations, but they're not disappearing. They're just moved to another space of like some additional parameters.
Effectively, this is what is happening. In general, this is what happens. For like what I'm going to present in the remainder, you see that this issue kind of goes away. Everything basically becomes I can just do the integrals in the end without actually having a problem. Um, but it's a fair comment that you're essentially just reducing the dimension you're doing the integrals in. Um, but I guess this is also the same if you like SUSY localization, it's the same kind of issue you have there as well.
Yeah, but they're also like not completely disappearing. They're just moving to some like integration in some like another space, right? Here, like you have still integral.
Yes, but the space that you end up with is easier, I'd say. It's just like flat space integrals.
Hmm. Okay, thank you.
Okay. So in the last 15 minutes, I'm going to try and tell you some applications of this which are actually useful. And what we're going to apply it is to Roman supergravity. So we're going to work in Euclidean space. So we don't have these issues with T being R rather than a circle. And what we're going to take is some particular 6D gauge supergravity theory. The details of it aren't super important. You just have some metric, a dilaton, some SU2 gauge fields, and some 2 potential. It doesn't really matter. We're going to impose supersymmetry. So we have some killing spinor equations. So they schematically look like del mu epsilon plus fluxes is equal to 0. And by imposing this, you get some conditions, which are called torsion conditions. You should construct forms by epsilon bar or epsilon bar C, wedge multiplied by a number of gamma matrices, wedged again with another epsilon. And this is basically the form on your space-time. And by basically just using this equation on this form, you get a set of differential equations on forms rather than just this equation on one spinner. So you can plug this, you can do this kind of old trick, and this was done in this paper by Alday, Fluder, Gregory, Richmond, and Sparks. And one of the nice things that you have, and it's pretty common when you have these supersymmetric geometries, is that you end up with a killing vector, psi, which is basically imposed on you by supersymmetry. You also get all these torsion conditions, so the exterior derivative acting on a set of forms. And for example, one of them is this. So P is some particular bilinear that you construct out of these spinor. It's just this thing here. It's just a scalar. X was the dilaton. And what you find is that this is equal to minus the 1 over square root 2 contraction of this killing vector into the gauge field for your S2, the field strength of your gauge field for your SU2 gauge fields. So you get a set of conditions. And the nice thing is that, particularly from this one here, is that you can basically construct the polyforms by just using these torsion conditions. So before I did it in the examples of the S2, I basically needed to construct the metric and work backwards. But essentially, supersymmetry kind of gives you these polyforms for free. We don't quite understand why, but it does. And now we can just start running the same machinery. So we have to ask again, what are these possible fixed points? So we have some 6-dimensional space, so we can have 0, 2, or 4-dimensional spaces. But you have some very generic things that supersymmetry tells you. For example, supersymmetry tells you, in general, epsilon is not chiral. But when you go to these fixed point sets, it becomes chiral of either, it can be either chirality. And what's more, if you have something like this F0, and I split it into these 3 copies of R2, we have these nice projection conditions on these spinners on each of these copies. So this sigma I is either plus or minus 1. And you have this nice projection condition. So you can plug all of this in. There's a lot of gory details, which takes maybe 10 pages, 10 or 15 pages in the paper. But those details aren't super important. But what you end up with, if you compute the on-shell action, so it's just, I take the action, I plug on what would be a solution, and I compute, you get this nice result here. So this is your dimension 0, dimension 2, and dimension 4 pieces. These sigmas are precisely these ones here from these projection conditions. This is just the product of the sigmas. And these epsilons are the weights that you get from your BVAB formula. So the nice thing is that this should hold, this is true, I should say, for any solution you could cook up for Roman supergravity. If you compute the on-shell action, it could be computed by this. So what you have to give are, you have to give me these sigmas, you have to give me these weights, and you have to give me these first Chern classes of these line bundles, and then I can just give you the computation. So a small technical piece. You may have noticed that there's also the C1 or Fs appearing. These look kind of like free things, but if you work out what conditions you need to impose on a spinner to be well-defined, for example, you find that if I take the integral of this C1 of F for a 2-dimensional fixed point set, I can actually compute it in terms of the line bundles C1 and the Euler characteristic of the surface that is being kept fixed. So this means I can plug this into here and it's fully generic in that I just need to give you the C's and the C1 for L's. This is just topological data. A similar thing happens for this dimension 4 fixed point. I could basically eliminate this term here, but not this term through looking at the spinners to be well defined. So what you find in the end is that the contributions from dimension 0 and dimension 2 are purely topological. They have no extra information you need to put in, like the magnetic fluxes that you have to impose. For dimension 4, you may have to impose some extra information about what magnetic fluxes you have through the solution, provided it satisfies this constraint. So let's just do one or two examples. So the first example we're going to do is I'm going to look at a 5D superconformal field theory. And what I'm going to do is I'm going to compactify this on a Riemann surface. So I get some 3D CFT. And then rather than just putting the 3D CFT on a round 3-sphere, I'm also going to deform this 3-sphere. So the conformal boundary for this would be S3B times this Riemann surface. So you should think of this as some asymptotically ADS6 solution in Euclidean signature with this conformal boundary. But what we really need is the information in the center of this space. And there we can take M6 to be of this form, R4 times sigma G. So again, we do the same thing as before. We write R4 in this nice splitting of R2 plus R2. We introduce these phi I coordinates, which are rotating each of the two copies. And just to make the example as simple as possible, we take this C1 of L to be 0. So we take our killing vector to be the linear combination of these two phi i's. And now the fixed point set is precisely going to be at the center of R4, and it's going to leave the whole Riemann surface untouched. So we're going to get these two-dimensional fixed point sets. So here was my formula from before, and now I just get rid of everything that I didn't need. So we have no dimension 0, we have no dimension 4. We set the C1 of L's to be 0, so we just get left with this term here. And from this technical information, what we have is that the integral of this first-term class of the SU2 gauge fields is precisely just the Euler characteristic of the Riemann surface. So I can just plug this all in, and this is the result I get. So this is quite nice. It matches all the field theory results that are known. And it was very easy in the end. I just plugged in a few things, and I basically just kept plugging stuff in. It was very simple. I didn't have to solve any equations of motion, and we have some exact result. So this contribution here is really because you have a deformed 3-sphere. This contribution is just because you've wrapped it on a Riemann surface, and this is just the free energy of your theory if it was placed on an S5. So it's a very simple result, and it came out very easily from our results. So I'll show you one more. I'll leave the third one as bonus material. So here we're going to consider what we're going to call like black saddles. So these are like Schwarzschild-like solutions in 6D, where you have something which is like R2 times some 4 manifold B4. So the conformal boundary is S1 times this B4. And this would be dual to some 5D SCFT, which I'm going to place on this B4 and just compactify down to some 2D theory. So we're going to take this killing vector to be the one that rotates in the R2. And then the fixed point set is just going to be this B4 at the center of R2. And again, just to make things nice, I'll set C1 of L to be 0. And then I just plug everything in. So this goes, because there's no 0 or 2. And we're just left with this final contribution from the dimension 4. So the nice thing now is that because I've eliminated this C1 of L, just by my choice, I didn't have to. What I have is this nice result which links the integral of the first Chern class of this F squared to topological invariance of my B4 manifold. So this is just the Euler class of B4, and this is the signature of B4. And it means I can now eliminate this term in terms of topological stuff. And what you end up with is this very cute result here. So this is purely topological. I didn't have to do anything else. I just had to specify some topology about my B4 in terms of this Euler character and this signature tau. So no one has quite noticed this result before, in field theory at least, or even gravity solutions. So for gravity solutions, no one's really computed these things, except for specific examples. And one of these specific examples is you take the product of two Riemann surfaces, and then you can just compute these topological invariants. So the signature vanishes, and the Euler is just the product of the Eulers of the two Riemann surfaces. And what you end up with is this nice result here, which we can match with some supergravity solutions already. So how many minutes do I have left? Is it 3?
Yeah, yes, roughly 3 plus questions, 15 minutes for questions.
Oh, okay. Should I skip this one? It'll be very quick or not? Your choice.
Well, it's okay, you can cover it.
Okay. So the final example is I've been ramping up the difficulty a bit. So now we're going to do this. So this is just fancy words for R2 plus R2, fibered over an S2. And these P's just tell me how I'm fibering it. So you should think of this as just, I take this angular coordinate on R2, and I gauge it with some gauge field on my S2, which has magnetic charge minus P over the S2. So it's very simple. It's just fancy words for something kind of simple. So the Killing vector now is going to be a combination of the phi's on these two bundles and also the coordinate rotating the S2. So the fixed point set is going to be at the center of each R2 and at the poles of the S2. So we get 2 fixed points. These Chern numbers that I've been setting to 0 so far are now no longer 0. They're these PIs appearing here. And then I also have to pick out the weights. These are a bit more difficult, but we could resort to some toric geometry. So you can draw this toric diagram for this. So I'm not going to explain it very well, but roughly these V's are defined for you faces where a vector shrinks. So we have 4 of them. And really what you should think of it as is there's a 2-sphere here, and this face where V3 is vanishing is the North Pole, and this face where this V1 is vanishing is the South Pole, and each of these V2 and V4s are where the circle is vanishing for either O minus P2 or O minus P1. So at each face, we also have to give one of these sigmas, which are these projection conditions. So we see that we have sigma 1, sigma 2, and then we have a choice for different choices at the north and south pole of the 2-sphere. So you can compute all these weights using this toric data. I'm not going to go into it, but this is what you end up with. So it's quite simple. It's just the B's that you had before for the North Pole, and they're kind of shifted by this B3 at the South Pole. You no longer have dimension 2 or dimension 4 fixed points. They're just all dimension 0. And what you end up with is this cute formula here, where you're going to get 2 sums of this by plugging in these weights and these sigmas. So you get this somewhat ugly looking formula at the end. But this is now a completely new result. No supergravity solution nor field theory results for this. So this is a nice prediction of what you can have. And it has these nice form of like gravitational blocks, or if you're more of a SUSY localization person, more of these like holomorphic blocks. So you get a contribution here and a contribution here. So these sigma 3s, I have a north and a south one. I have a choice on to take where I pick them either the same or I put a different sign between them. And if you're familiar with this language, this is whether you have a twist or anti-twist. You can also do some nice things. So if you set the PIs to 0 and this B3 to 0 and the genus to 2 in the B and the P's to 0 here and the genus to 2 in our example 1, this all reduces down to the same thing. This is kind of non-trivial because here you just had contributions from 0-point fixed sets, where from the other one you had just contributions from the dimension 2. So it's a nice non-trivial check that you have the correct results. But this just exhibits how powerful this is, that we can get these nice new results with barely any additional information. We just had to pick some topology, which is quite simple in the end. And we just had to plug stuff in and we get this prediction for supergravity and field theory. So just to conclude, equivariant localization gives this powerful method for computing certain holographic observables. All we really need is some isometry to apply it. And if we have supersymmetry, this is basically always present. It's something to do with it's dual to the R symmetry. So we applied it here to Roman supergravity. We recovered some old results quite easily, but we also got lots of new predictions for results that can be compared to field theory predictions or even gravity solutions which haven't been constructed yet. So there are some hidden subtleties. I've just said this is the topology I want, and then just plug stuff in. So you could ask, do solutions actually exist? So we don't know of a good method at the moment to tell you that all these solutions exist. You could cook up some crazy stuff from this localization point of view. It wouldn't have a problem, but there probably won't be a solution for it. But this is kind of like a issue this kind of extremization ideas have. Odd dimension works slightly differently. So here I always picked the dimension to be even. Odd D is slightly more tricky. You basically need two U1s. And we used supersymmetry to construct these polyforms. So a natural thing would be, can you get away from just using SUSY to construct these polyforms? Is there a nicer way of doing this without just relying on supersymmetry? So there's many ways to extend this. If you're more interested in like precision holography, you may want to add in higher derivative corrections. There, the issue again is like, I need to find a solution, then I need to plug this into these higher derivative corrections, blah, blah, blah. This kind of gets rid of this issue. I just do the same analysis now, but I include higher derivatives in my Lagrangian. There's not really much different. So you can start adding different matter content. You could add in boundaries. So with Alice Lucia, who's in the audience, we looked at this from the point of view, or kind of the converse point of view. We looked at ADS4 solutions in massive type 2A, which are kind of dual to some extent this solution here. And there you have to basically add in boundaries to get the correct results. So I completely ignored boundaries in this derivation part, but you could add in boundaries and it all works well. And the final thing is, this is a very powerful technique. I could now add in infinitely many high derivative corrections to some theory. So can I actually get a better like exact matches with field theory? There seems to be some nice connection between what we're doing here and what field theory gives you in terms of these blocks and things like this. Okay, thank you, and sorry for going over time a bit.
Thank you, Chris. Questions?
Can I ask a very trivial question? Suppose you have
Yeah, of course.
an integral of a constant over two torus. Okay?
Okay.
So there is a S1 symmetry which rotates the torus, but the killing field doesn't vanish anywhere on the torus.
Mm-hmm.
So how does your formula applies in this case? That doesn't apply.
So here you wouldn't be able to use it strictly because there is no fixed point of your symmetry. However, you can now do a trick. You could know that in one direction, I can basically enforce a fake boundary. So I could cut the torus in basically cut the torus at some point, enforce this boundary, and then you could actually do this localization with having two boundaries, basically. So the only piece of information you would need there is the length. But this
Can
is
I
very
ask,
trivial.
yeah, can I ask the trivial question first? Your logic kind of applies that the integral is suppressed by factor e to the minus xi t times xi squared,
Yeah.
so it would vanish if xi squared doesn't equal to zero anywhere. So why doesn't it equal zero? Why doesn't your logic applies that the integral should be zero over a torus, because xi squared doesn't vanish anywhere.
Because in writing it like this, I made this assumption that at some point it looks like R2 because I have a fixed point. So there's an assumption in writing this point here.
Yeah, but the formula before that, yeah, this one, it has xi squared. You do not assume anything, but this integral, the second one, is suppressed by kind of e to the minus t times xi squared and t arbitrary.
For your torus example, you couldn't make this phi well defined. That is the issue
Okay.
there.
Okay.
There
Okay.
you'd have to so there's some subtle like global regularity conditions here, which for the
Mhm.
torus wouldn't work.
So I couldn't promote my constant to a form, which is
Yeah.
okay, and that's why you need a boundary. So
Yeah.
okay.
You can kind of fake this. So you could do a cylinder very easily. It's just you have a boundary rather than, but it kind of reduces to a trivial statement at that point because you're not actually doing
Mhm.
anything. You're just
Ah,
reducing along a circle and then you have an integral over a line. So,
okay. Thank you.
Well, I have a question. Well, probably with some thinking, it's quite easy. But like, let's say you have a metric and your form. So this is one piece of
mhm.
data, and another piece of data is what you are actually using for computations. So to what extent the map between the two is one-to-one? So can you reconstruct the metric and the form back from the data that
No,
you
I can't construct a metric from doing this. I can only compute the integrals. So I have less information than the metric, but this less information is enough to compute certain physical things that I'm interested in.
which essentially means that there can be metrics with different metrics with the same data that you actually,
Yeah, exactly. Yeah.
yeah, and they don't even have to satisfy any equations of motion, these metrics, right?
Yeah, so there's a subtlety in that because you've imposed all these supersymmetry constraints, the like putative solutions that you should have some knowledge of satisfying the equations of motion, but it's not 100% that they're fully on shell. They're like what we call partially on shell. So they satisfy some of the equations of motion.
Mm-hmm.
Sorry, they have to satisfy some of the equations of motion, but maybe not all of them.
Mm-hmm.
But it's a good point that there can be different metrics which give you basically the same topological data, but yeah, we would be blind to this basically.
Mm-hmm. Okay. Well, another question, it's more, I don't know, like history. So, is it true that what you are doing is just a bosonic version of supersymmetric localization? Or just there are
Uh,
similarities and this is
so
it?
so SUSY localization came after this. So originally this was done like in the 80s, and then people used this at some point to do partition functions in quantum mechanics. So you get your phase space and you can do these integrals over phase space using this equivariant localization. And then to do SUSY localization, people kind of Pestun basically understood how to do this equivariant one. And essentially, if you do the equivariant localization, I should have put a slide explaining it, but essentially what you do is that this is the queue for SUSY localization. And sorry, and this is basically the BPS locus. So there is a very close analogy to what you're doing. It's basically you're taking a bosonic symmetry versus a fermionic symmetry.
Yeah, so the supersymmetric one explicitly relies on this, right? It's just some sort of an extension.
Yeah, it's an extension, but they're actually independent. It's just they follow the same kind of logic.
Okay, thanks.
Yeah, the SUSY one does exactly this as well, where this is now basically the BPS state. And this here is modified by some Q exact piece.
Okay. So, any questions? Going once, going twice. Okay, perfect. Thank you again, Chris.
Okay, thank you.
Yeah, it was a very nice talk, and yeah, thanks for presenting to my group. Okay, so the recording will be made available online on YouTube, and yeah, can I ask you to send a slice of your talk so that I can put it
Yep.
on the page, on the seminar page? Okay.
Yep.
Okay, thank you.
Thank you.
Bye.